The first problem we'll look at is calculating the theoretical yield in grams. Here's a reaction with different stoichiometric coefficients that add some flavor to the problem solving. Take a minute and read the problem and consider my first step. It's important to appreciate how to read the chemical equation. 2 moles of chromium bromide, 3 moles of ammonium carbonate, 1 mole of chromium carbonate, and 6 moles of ammonium bromide. Think of it that way. The first step makes perfect sense. That is, first calculate the number of moles of each reactant you have. Then we go about predicting the amount of moles of product produced. Next, we'll use the balanced equation and the moles of each reactant to predict the quantity of the particular product produced. And one way to solve this problem is to determine which reactant is the so-called limiting reactant. And I like to do this by testing or checking each reactant. So first I'm going to check the ammonium carbonate. I do that by using all of the chromium bromide. So for 0.01 moles of chromium bromide, I need 0.015 moles of ammonium carbonate. I determine the 0.015 moles of ammonium carbonate by using the 3:2 stoichiometry. Using the 3:2 stoichiometry, I see that I need 3 halves, or 1.5 times as much ammonium carbonate as I need chromium bromide. That's how I came up with the 0.015 moles of ammonium carbonate. Well, if all of the chromium bromide is to be used up, there doesn't appear to be enough ammonium carbonate to react. I move on to the next reactant. Then I test the chromium bromide by consuming all of the 0.01 moles of ammonium carbonate. Using the 2:3 stoichiometry, I find that I only need 0.0066 repeating decimal, or I'll just round it off to 0.00667 moles of chromium bromide. The stoichiometry says I need 2/3 the amount of chromium bromide as I need ammonium carbonate. So 0.01 times 2/3 is 0.006666. Well, I have 0.01 moles of chromium bromide, so I have more than I need with regard to chromium bromide. So my conclusion is, what actually is going to happen is all of the ammonium carbonate will be consumed because it is the limiting reactant, and only 0.00667 moles of chromium bromide will be consumed, leaving behind 0.0033 moles of chromium bromide and theoretically 0 moles of ammonium carbonate. To determine the amount of chromium carbonate that is produced, I could use either the 1:3 stoichiometry between the chromium carbonate and the ammonium carbonate, or the 1:2 stoichiometry between the chromium carbonate and the chromium bromide. But whether I use the 1:3 or 1:2 stoichiometry, I need to reference the amount of moles that actually reacted. If I use the 1:3 stoichiometry, that is between chromium carbonate and ammonium carbonate, 1/3 of 0.01 moles of ammonium carbonate is the amount of chromium carbonate that is produced, which is 0.00333. If I use the 1:2 stoichiometry between the chromium carbonate and the chromium bromide, I'll use 1/2 of 0.00667, which is 0.00333. So what remains and what is produced is the final line. 0.00333 moles of chromium bromide remained. No ammonium carbonate remains, and 0.00333 moles of chromium carbonate are produced. And now converting the moles of chromium carbonate to grams, use the molar mass of 284 grams per mole to get 0.949 grams. And this is called the theoretical yield. I'd like to add to the previous problem, and that is calculate the molar concentration of the byproduct, ammonium bromide. If you understand calculations we've gone through in the previous problem, there's really just two more things you need to add. That is, to this last line, how many moles of ammonium bromide were produced? Well, you could simply use the 6-to-1 stoichiometric ratio between the products, because we know 0.00333 moles of chromium carbonate were produced. That means 6 times that amount of ammonium bromide were produced. So that's 0.01998. Then take that mole amount and divide it by the total volume solution. It should be approximately 200 milliliters. I say approximately because of the precipitate that form, but 200 milliliters is a real good number to use. So we convert that to liters. It becomes 0.2 liters, and so molarity is moles per liter. Divide the numbers and you'll determine that the molar concentration of the byproduct is 0.0999 molar.